There's no response from anybody. What does that mean? Are you guys there in the class? The 31 members whom I'm able to see. 41. Oh, great. Number is increasing, but there's no response from you people. See, response doesn't indicate you have to tell me yes all the time. You can at least tell you didn't start or you didn't see or you didn't do. Anything can be the response, right? I'm talking from this side and I don't get any answer from your side is literally not good. We should feel that sometimes. I feel, let's see if at all we can go for any seminars that you can give. When the other person from is listening or not, if you don't know how it feels, you should know.
Started, ma'am.
Yes, Shravanti, started.
Yes, ma'am.
You're getting how to solve it.
Yes, ma'am, but at last we are getting 8 into 8 matrix, ma'am. That we don't know how to do.
Okay, that's it. That is why I mentioned you to check from the textbook. The inverse of that matrix is given in the textbook.
But explanation is not given, ma'am. Only that matrix is given.
See, if you have the matrix with you, that's enough. While you're solving your problems, if you have the matrix with you, that is more than enough, because how do you reach to the matrix is not important for the examination point of view. See, 8 by 8 matrix, to keep solving it will take ages. All right, when we are going for the reason for giving the higher order problem is when we are going for unit 4, you're going to have higher order elements with you. In such a case, how are we going to reach to the matrix just for an practice I've given? All right, how do you have if you sit solving for the 8 by 8 matrix, that is going to take ages now. You can try if you have free time. You can try doing
We
that.
should remember, ma'am, that matrix.
Sorry.
We should remember, ma'am. Uh,
Actually, yes.
okay, ma'am.
All right. Good that you have started. All right, we'll start with today's class. Right, what is the last topic did we discuss? What is the last topic that we discussed?
Strain displacement matrix.
All right, it is just that we only started that, but we didn't complete it. All right, so we will start with that topic again. All right, so let's do this. Maybe I think we stopped at the triangle figure, right? So if at all previously, if somebody is not there in the previous class, you may please note down today's heading. It is going to be strain displacement matrix. We are going to start strain displacement matrix. Right, I'll share the screen with you now. What is happening? Just a minute, it is taking a little longer to open. All right. I'll share the screen. Mustafa, please let me know if you're able to see the screen. Am I audible enough? Because I'm not getting response from your side. Mustafa, is there an issue with your mic again?
No, ma'am.
All right. All right. Can you see the screen now?
Yes, ma'am.
Okay, good. Right. We'll start with today's session. Right. Strain displacement matrix. When we have to solve the problems, this matrix is gonna have a huge role because our basic unknown is displacement. So when we have displacement, if at all we have to reach to the stress parameter, we have the relation between stress and strain. All right, and we have the relation between strain and displacement. So when we know the displacement matrix or the basic unknown displacement, from there to the displacement we'll um, will relate it to strain, and finally we'll relate strain to stress. That is how it goes. All right. From strain displacement matrix, if at all you were not there in the previous class, note down the case how it goes. At any point in the CST element, please note down. At any point in the CST element, at any point in the CST element used for plane stress or plane strain problems, used as plane stress or plane strain problems, there are three strain components. There are three strain components. That is epsilon x, strain in x direction, epsilon y, strain in y direction, and gamma xy, strain in the xy plane. Alright. Now from the very first class, what we have seen in the unit 2, in the unit the topic comes under unit 2, the strain displacement relationship. In that, what is epsilon x? Is epsilon x is dou u by dou x, the displacement in x direction. Alright, dou v by dou y, and dou u by dou y plus dou v by dou x. Please verify from unit 2 notes if at all you don't remember this. All right, that is why that is the basic. Unit 2 will become the basic concepts that you have to remember, so that we can solve any kind of problems or we can analyze any kind of problems in the coming units. All right, now if we already know, if the displacement matrix U Now, because this is a 2D element, we are going to have displacement in both the directions u and v, that is in x direction and in y direction. So we have the relation of uh, displacement at any point in the element with the nodal displacement, that is through shape functions, right, which we already derived in the previous classes. Let us take that equation here. Is this the equation what we have seen in the previous class? Shape functions for a CST element. Did we see this? I need response. I cannot go like this, you know.
Yes, ma'am.
Right. So for this case, now we have from the previous from the oh god, right. Now from the strain matrix we have dou u by dou x, dou v by dou y, and then finally dou u by dou y plus dou v by dou x, right? If at all the u matrix here, what we have u comma v, if we take that into this equation, all right, we are going to end up here with this matrix, all right, dou n1 by dou x, dou n2 by dou x, dou n3 by dou x, 0 comma 0 comma 0, 0 0 0, partial differentiation, right? So dou ny dou y, dou n2 by dou y, dou n3 by dou y, and here when it comes to u to v and v to x, u to y, u with respect to y and v with respect to x, in such a case dou n1 by dou y, dou n2 by dou y, dou n3 by dou y, dou n1 by dou x, dou n2 by dou x, dou n3 by dou x, this whole matrix into the elemental displacement matrix, that is u1, u2, u3, v1, v2, v3. Understood? How did we get this? We have just substituted, taken this equation into this equation because there was partial differentiation. Because there was partial differentiation, the partial differentiation is going to come for the shape functions which have the variables. All right. Now, if at all this equation, this whole of this matrix have to be solved, all right, we need the values of shape functions n1, n2 and n3. Here differentiation is carried out only for these three elements, these three equations, we can tell shape functions. All right. Now look here. From the go to CST element derivation, shape functions of CST element derivation, and write down what is the equations for n1, n2, and n3. That's your part now. What is n1, what is n2, and what is n3? Anyone? What is n1?
A1 plus B1x plus C1y by 2a.
Right. C1y by 2a.
2a.
Right. And n2 and n3 also follows the same pattern. If at all I have to remember it a little bit easier, what I'll do, because it is n2, I'm going to get all the two terms. N3, A3 plus B3x plus C3y whole divided by 2a. Right? Now, here what all terms we have? If you see in the matrix, look here. We have n1 with respective x, n1 with respective y. All right. So partial differentiation of n1 with respect to x ones and with respect to y. We have two different cases. All right. See, with respect to nx now. With respect to x, if I have to do, what will this become? b1 by 2a. Is it not? Partial differentiation. A is a constant, so 0. Y is a constant when it is with respect to x, so 0 by 2a. And what is for n1 by dou n1 by dou y? What will that become? C1 by 2a. Is it not? Guys, are you there?
Yes, ma'am.
Now
Yes,
do it
ma'am.
for n2 and n3 also. Do it for n2 and n3. Do the partial differentiation with respect to x and with respect to y. Did you all also get the same values? Please cross check. Please tell me a yes once you have got all the 6 terms.
Yes, ma'am.
Oh, good. Now, if at all, now we have all the terms in the matrix for the previous equation. All right. Therefore, the strain matrix will be equal to 1 by 2a into what is first term? N1 dou n1 by dou x, right? That term is b1. I have taken 2 by 2a common, and the next one will be b2, and next will be b3, 0, 0, 0. Follows with the same thing now. C1, C2, C3. Here C1, C2, C3, B1, B2, B3. And what do we have here is elemental displacement matrix. Is it not? Have any doubts? How did we reach to this matrix? Anybody?
No, ma'am.
Right. Now, if we clearly see this matrix here from 1 by 2a until this point, let us call this as matrix B. If we see this clearly, what is this B matrix doing? What is this B matrix doing? It is relating the strain in the element with the elemental displacement. What is it doing? Elemental displacement matrix, or you can call that as nodal unknown matrix, right? So the B matrix is relating strain with the displacement. That is why this B matrix is called strain displacement matrix. Strain displacement matrix. Strain displacement matrix. All right. So we can write this as a whole like B, sorry, epsilon matrix is equal to strain displacement matrix into dou E. Let us take this as equation number 1. All right. Are we clear so far? Are we clear so far? Until this
Yes,
equation, you
ma'am.
have
Yes,
any
ma'am.
doubts? Any doubts until this point?
No.
Now, what is B matrix here? B matrix is equal to, you can write this as where B matrix is equal to 1 by 2a into b1, b2, b3, 0, 0, 0, c1, c2, c3, c1, c2, c3, b1, b2, b3. Now, either you can try and remember what is B1, B2, B3, C1, C2, C3. However, for shape functions of a CST element, we know what are all these terms. All right. From the determinant of that 3 by 3 matrix, we got all these values. All right. Determinant, not inverse, adjoint from the adjoint matrix. All right. If in any case you don't remember, all right, how what is B1, what is B2, and what is B3, in the previous class we have seen taking the equation, taking the figure directly. All right, first from the because we have already derived it, We can take it down directly. What is B1? What is B2? What is B3? Next is
Excuse me, ma'am.
C1. Yes.
Ma'am, can you write little big, ma'am?
Little more. I'll
Yes,
increase
ma'am.
the
I'm
ratio
already
of
zooming it,
this.
ma'am.
Okay. I'll zoom it. One second. Is this okay?
Yes, ma'am.
Anybody else? Any issues in seeing the page? Is this okay now?
Okay, ma'am.
All right.
Okay, ma'am.
Okay, fine. Good. Now, what is B1, what is B2, and what is B3 here is, if at all you go for the derivation of shape functions in the CST element, you can find these values. Even if you don't remember, B1 is y2 minus y3, y3 minus y1, y1 minus y2. C1 x3 minus x2, x1 minus x2, sorry, x1 minus x3, and x2 minus x1. Just in case if you have to remember, B1, when you will get the other two terms of y2 and y3. You will not have the y1 term. Alright, and it goes in the cycle 1 2 3 2 3 1 3 1 2. It goes in a cycle format for the B case. Alright, for the C, when it is C1, you will not get the term 1 in the X, but it is going to be x3 minus x1, not x2 minus x3. That is how the cycle goes. Alright, please note it down and give me a yes once you're done. Are you done with the equations? Are you done with the equations?
No, ma'am.
Alright, do it.
Completed, ma'am.
Right. If the same equations has to be taken down from the figure, sir, if at all we have to remember considering from a figure of a CST element, taking that as if you remember what nodes we have taken in the first case, we have to consider the same nodes again, because the values of shape functions what we have taken is exactly from the previous case, right? Now this is a x and this is y. All right. Now when we have to uh, see, when we are going for the closed structure, what is happening here? We have the difference. What are the vertices we have here is x1, y1, we have x2, y2, and we have x3, y3. All right. Now, based on that, when we have to go, I'll better change another color for this. Right. What is the difference between these two here is B3. B3 means y1 minus y2. That is the difference here, this part. That is because when we are going in the cycle, when we take it in this format. I'll write down the whole values first and tell you what is the cycle we are taking. Y2 minus y3. All right. And then here all y I'm finishing it first. It is y3 minus y1. All right. When it comes to y, we are going in this direction. All right, closed format. We are going into the closed format. When it goes in this closed format, y1 minus y2. This is how we are going. Y1 to y2, then y2 to y3, and then y3 to y1. This is how the cycle goes. All right. When it comes to x, let us take this one. When it comes to x direction, it is C3. So y2 minus y1. It is x3 minus x2. And here it is x1 minus x3. The cycle closed circle. So closed circuit. So we are coming in this direction. All right. Please check. We are going in this direction. X2 minus x1. And then x1 minus x3, x3 minus x2. This is how you go. You're trying to go in a closed format. See, if at all you directly remember what are the values we have taken in the shape functions, we don't have to go for all these cycles and all. But this is the format what we generally take. All right. Any doubts in strain displacement matrix until this point? Any doubts in strain displacement matrix? Guys, are you there in the class?
Clear.
No doubt, ma'am.
Okay, right. Then we'll go for the next topic. Very, very important. Very, very important. So what I'll do, I'll start a new one. All right. We have unsaved changes. All right, take down the heading as elemental stiffness, elemental stiffness considering virtual displacement, considering principle of virtual displacement. If you have the syllabus copy with you, the topic names this way: using principle of virtual displacement, the determination of elemental stiffness of a CST element, that is 3-noded triangular element and 4-noded rectangular element. That is what is mentioned in your syllabus. Alright, we are going to start that today. Very, very important. What all problems what we are going to get, and previous year papers also, if you see, we have problems of CST element or 4-noded rectangular element to find out what is the stresses in the element. We get it, we solve it using elemental stiffness matrix only. Alright, so let us take the heading elemental stiffness using principle of virtual displacement. Alright, let me ask this question to you. What is principle of virtual displacement? Many members of you have already written this in your midterm. What is this principle of virtual displacement? I need answer from your side. Principle of virtual displacement. Anybody? Principle of virtual displacement. Guys, are we still connected? Are you there in the class?
Ma'am, a body is in equilibrium if the internal virtual works equal the external virtual works for every kinetic.
Every?
Uh, Kinematically admissible
Kinematically what?
displacement field.
Right, kinematically admissible displacement field. So in which method did we look into this virtual displacement is Galerkin's method. Just in case if anybody don't remember, please go back to Galerkin's method and check what is the principle of virtual displacement. So we are going to take that principle of virtual displacement into determination of elemental stiffness for the element. All right, thank you, Hadi. Now, from the previous equation, that is in the previous derivation, that is strain displacement matrix, taking equation number 1 into account. All right, I'll write it in bigger now. From equation 1, strain displacement matrix, we have, see, either I call it as DE or delta E or UE, it does mean elemental displacement matrix only. All right, is it not? So we know just the previous one what we have solved. We are going to take that directly here. All right. Guys, if at all you're unable to hear me or is there anything that you have to say, please unmute yourself or raise your hand so that the moderator will inform me. All right. Any doubts, you stop and ask. If the voice is not clear also, please make sure you stop me and you ask. All right. Now, what is this equations we have here? What is this B matrix? What is this B matrix?
B1, B2, B3.
No, no, no. The name of the matrix is enough.
Strain
What is,
displacement.
Strain displacement
yes, strain
matrix.
displacement matrix. Because we are doing a derivation, we might not know if the derivation is asked. So let's do the derivation properly. All right. So this is strain displacement matrix. And what is DE? What is DE?
Elemental
Yes,
element
elemental displacement matrix. Good. Elemental displacement matrix. All right. Now let, write down please, let, what is this matrix? Stress vector.
Strain
Let us, I'm asking you what matrix is this? Let's stress the sigma matrix. Sigma matrix is the vector of stresses, vector of stresses. That is the stress matrix, that's all. Vector of stresses corresponding to the strain matrix epsilon. All right. So now we have three terms with us. We have three terms with us. So the elemental stresses can be expressed as, write down, elemental stresses can be expressed as, how is stress and strain related when it comes to matrix form? How is stress and strain related? Anybody? Stress strain relationship from unit 2. How is stress and strain related in unit 2? You have already done this in your mid 1 also. Come on, none of you.
D.
Yeah, what is that called? Who was that who answered? Who was that? Shrikant, okay. Your voice is not louder. It is D matrix. Relative constitutive matrix. Remember this? Relative constitutive matrix D. That is the relation between stress and strain. You have to go back to unit 2 if you don't remember this. Alright, we have solved it. Right. Now considering this, from equation 1, we have epsilon, right? So just write that epsilon here. D matrix. What is epsilon from equation 1? It is B matrix into DE. So let us take this as equation number 2. Did you understand what did we do? We just substituted the value of epsilon from equation number 1. That is why very first in the beginning we have written what is equation number 1 here? Epsilon matrix. So we have taken that epsilon matrix and substituted that in equation. Alright, stress strain equation. Alright, that is equation number 2. Alright, now what is this D matrix also? You may please note it down. What is the D matrix here? D matrix is the relative constitutive matrix. Relative constitutive matrix. Okay, write down. Now it is necessary to derive. Now it is necessary to derive equilibrium condition for an element. Equilibrium condition for an element. Now, when we speak about the equilibrium condition of the element, we are trying to consider all the effects, all the external loads that are going to affect the element. Beginning of the unit 2 or beginning of the sessions, we have seen we have three different parameters that we considered. That is, we will have body forces, we will have traction forces, and what is the other one? Also point loads. All right, so point loads, we will eliminate that for time being. We will consider what it is when it comes to traction forces, all right, and the body forces. All right, so we'll take that into picture, into account, and we'll write it down. For the equilibrium, did you write this? It is necessary to derive equilibrium condition of the element. Did you write that?
No, ma'am.
Write it down. It is necessary to derive equilibrium condition for an element. Therefore, therefore, considering the principle of virtual displacement. Principle of virtual displacement. What do we have here is the equation Where did we see this equation? Did we see this equation anywhere? Did we see this equation anywhere? It is on the screen. You can write it down. First, I'm asking you a question. You please respond for that. Did we see this equation anywhere? I'm asking you something, people. I said in the beginning of the class, please respond. Even if it is a no, that is okay. It is not necessary that you remember everything. I am not asking you, you have to tell a yes.
Ma'am, it is potential energy in 3D body.
Potential energy. Are we trying to use the principle of potential energy here or with principle of virtual displacement?
Okay.
Check it properly. I wrote principle of virtual displacement. Is it not? So in the Galerkin's method, look into the end equation when it is about the elastic problems. You'll find the equation there. Look here. Remember this equation? Equation number 10 in Galerkin's variational form of 3D stress analysis. Are you able to see the screen?
Yes, ma'am.
Remember this equation here?
Yes, ma'am.
See. If you see this, here we are not considering the point load into picture. Alright, we are not giving any external point load. Without giving the external point load, what are we left with? We are left with the internal stresses, internal forces that are happening, and this is the body forces, and this is the surface traction forces. Right? That is the same equation that I have written it over there. Alright? Got the point? Guys,
Yes, ma'am.
very important derivation. If you have doubt, you have to ask. Alright? So, taking that equation into account, we are going to solve it. Now, let us take this as equation number 3. Alright? Now, if you check this equation clearly, alright, here we have strain displacement equation and stress, not strain displacement, sorry, strain equation, strain matrix and stress matrix. All right. Now here it is not directly epsilon matrix, but it is delta epsilon. All right. Delta epsilon. All right. Delta epsilon is the virtual strain matrix. All right, and here we have delta u. When it is about u, it means it is elemental displacement delta u matrix. All right, or we can call that as delta e. Here we have delta u first. We'll talk about this one. Delta u here is virtual displacement. At some point we will come to UE later, U matrix later. First we'll see what is this virtual displacement first. Okay, virtual displacement. From equation 2, what do we have? We have epsilon matrix is equal to B matrix into DE. Is this equation 1? It is equation 1 actually, not equation 2. From equation 2, from equation 2. Now see, since this one be strain displacement matrix depends upon the, what is strain displacement matrix here? Strain displacement matrix is the uh, direct, what all terms we have in strain displacement matrix is the terms from the vertices of the CST element. All right, it is nowhere related to worthy uh, variations in the epsilon matrix or in the D matrix. It is independent of this. All right, we have all B terms, C terms, that is X terms and Y terms. All right, so please note it down. Since B matrix since B matrix is independent of displacements, since B matrix is independent of displacements, the virtual strain due to due to due to virtual displacement dE, due to that is, I'm making this virtual and I'm making this virtual here. All right, due to virtual displacement dE is given by B matrix is independent, so it is going to remain the same. All right, we'll take this as equation number 4. Got the point here? Got the point here?
Yes, ma'am.
Right. Now what is the next one we have? We have the new term. What we have is virtual displacement at a point U. All right. Now if at all we have to reach to this one, first what we have U matrix. What is U matrix? Displacement at any point is equal to shape function into nodal displacement matrix. All right, if you clearly see N matrix, again the shape function matrix is independent here. So what will happen? Again this will go as virtual displacement at any point will be equal to shape function into, let us take this as equation number 5. Whether it is called as UE or DE, it is same. It means elemental displacement matrix only. Either you call that as DE or UE. Got the point? Are we clear so far until equation number 5? Do you have any doubts? What all matrices we have seen till now, and in the whole of this unit 3, we are trying to take all of those equations for this single derivation. Please remember. All right, shape functions equations, strain displacement equations, all those things we are considering here only. All right, shall we move forward? Shall we move forward?
Yes.
Yes,
Right,
ma'am.
write down. Substituting equation 4 and equation 5, substituting equation 4 and equation 5, substituting equation 4 and equation 5 in equation 3. What is the whole equation we are going to get? This is big, but okay, we can now done. Let us take this as equation number 6. Here when it is about surface, this becomes NS. Let me write this little bit clearly. This is NS. Alright. Substituting equation number 4 and equation number 5 in equation number 3, we are going to get equation number 6 here. Alright. Here we have only one new term. If you clearly see, that is NS matrix. NS matrix is shape function along the boundary S1 where forces are prescribed. All right. Did you note down equation number 6? Did you note down equation number 6?
Yes, ma'am.
Anybody who you want me to wait, or shall we go forward? No response from your side, so I'm going forward. Right. Since the variation in the nodal displacements, write down, since the variation in the nodal displacement are arbitrary, the equation 6 becomes becomes equation 6 becomes since the variation in the nodal displacement since the variation in the nodal displacements are arbitrary, equation 6 becomes, write down, I'm writing down what equation 6 becomes. What happened in the equation 6? From equation 6, what is the change that you see? Virtual displacement, nodal displacement here is arbitrary. So we have eliminated that term. Is it not? From equation 6 has become in this format. Alright. If we
Yes, ma'am.
look, right, thank you. If we look this carefully until this section, this one whole here is the forces, right? Body force, traction force, all this side or the RHS side is completely forces. All right. And here we have displacement, elemental displacement we have. All right. When forces and displacements are related in this format. What do we have here is stiffness. Is it not? What do we call this? K. How is force and displacement related? With respect to K, right? So K elemental stiffness into elemental displacement is equal to elemental forces. Did you get this point? Stiffness is equal to force by displacement.
Yes, ma'am.
Right. Now, here we have in this format that forces are on the RHS side and stiffness into displacement in the LHS side. So what will this become? KE. Here is the stiffness matrix. Oops, sorry. Stiffness matrix of the element. Right? Now what is that stiffness matrix of the element we have from the uh, equation? Let me write it down clearly. K is equal to integration with respect to V B transpose D matrix B matrix into dV. All right, this is the elemental stiffness. This equation what we have here is the elemental stiffness. All right, now if at all force is asked, force matrix, what is the force matrix we have? Anybody, what is the force matrix we have? What is the force matrix we have here? None of you are speaking. Are you people there in the class? Integration V n inverse body force dV plus surface traction, integration with respect to surface traction ns transpose surface traction matrix into ds. What is this one we have here is force matrix, or you can call that as consistent load vector of the element. What is this? Consistent load vector of the element. You can call that also. What we can call this as? Consistent load vector of the element. Any doubts so far until this point? Any doubts? Guys, are you still with me in the class?
Yes, ma'am.
Right.
Yes, ma'am.
Right. Thank you. This is very, very, very important. Elemental stiffness matrix. Elemental stiffness matrix. When you have to solve the problems, you have to remember this equation. All right? Please note it down. Are you done? Are you done until this part?
Excuse me, ma'am.
Yes.
Ma'am, equation after 6 becomes after that I did not write, ma'am. Network problem. So can you show it, ma'am?
Right. Are you able to see?
Yes, ma'am.
Right. Others? Are you done until the force matrix?
Yes, ma'am.
Okay, please note it down. The above equation of equilibrium, the above equation of equilibrium is to be assembled is to be assembled for entire structure and the boundary conditions are to be introduced. The boundary conditions are to be introduced. Then the solution for then the solution for then the solution for equilibrium equations then the solution for equilibrium equations results into nodal displacements nodal displacements of all the nodal points of all the nodal points. Are you done? Are you done? Are you done,
Yes,
guys?
ma'am.
Right. Next point. Once the basic unknowns are known, once the basic unknowns are known, once the basic unknowns are known, then the displacement at any point, at the displacement at any point can be obtained by can be obtained by the equation obtained by the equation u is equal to n into dE. U is equal to n into dE. Then then strains from epsilon is equal to b into dE. B into dE. And then finally stresses from sigma is equal to d into epsilon. Understood? That's the end of the concept. Are we clear so far? Are we clear so far?
Yes, ma'am.
Any doubts until this point? Any doubts until this point? Anybody? If you have any doubt. No? Right. So here, what all derivation part we have from unit 3 is completed. All right. In the next class, we will solve a problem. How are we going to reach to the U matrix from U to epsilon, from epsilon to sigma? All right. How are we going to solve the problem based on the elemental stiffness? All right, that we'll see. What we'll do is we will directly try to solve a previous year question paper problem. All right, once we'll take a small problem first. Then from the previous year question paper, we have a problem like this from the CST element. Considering the elemental stiffness matrix, we have to find out the stresses. All right, we have a plane strain problem, I guess. Yeah, plane strain problem that we'll see in the next class. All right, we don't have class tomorrow because it's a holiday, but Friday we have a class in the morning session. All right, make sure you're present in that because we expect such problems much in the externals. All right, because we expect that in the external, you might expect that also in the internal. All right, it's very important that you be present in the class. No classes will be repeated. I'm seriously insisting you to attend every class. All right, no class will be repeated. You have to come back to the video sessions and see. All right, we have only 1 month left to complete whole of our syllabus. All right, once we solve the problem, there is a topic called discretization of the continuum. All right, we have a little aspects to look into it. Once we see that, unit 3 is completed. All right, maybe another little
Ma'am,
concept
put
is there.
this videos.
Sorry.
Hello. Ma'am,
Yes,
put these videos on YouTube, ma'am.
yes, I'll do that. Last classes, because of the internet issues, the recording was not proper, so I'll make a new video uh, alone. So because I cannot make the meeting and do it, I'll post the last 2 classes later. Today's class I'll post it today itself. All right. uh, what was I telling? Yeah, there is another topic like elemental stiffness for the rectangular element also we have to solve it. That is a little concept. If we see that we are done with unit 3, we can directly go for higher order elements. That is in the unit 4. Alright, isoparametric concept is there and higher order elements also we have to solve. Alright, Gauss-Jordan method, Gauss quadrature, everything that Jacobian matrix and all will be there in the unit next unit. Alright, somebody unmuted themselves and it is creating a disturbance from me. Moderator, can you please look into that? Alright, I'm taking the attendance now. Who all were not there at the time of the attendance in the beginning of the session, you will not get both the hours attendance. You're going to get only 1 hour attendance. Alright, I'll stop the recording also.